For the next 3 lectures or so, I'd like to talk about shaders, give a little more detail on GLSL, look at the execution model for the shaders, and look at more detail at what they can do and how we transfer information between the shaders and the application program. So what we'll do in this first part is look just a little bit at a vertex shader, a fragment shader again, and at the end of this whole thing, we'll have finished our first program in all the necessary detail. But before that, I want to say a few things about all the things you can do with shaders, that many of which you were not able to do before with or without shaders until shaders became available and became programmable. So some very simple examples are morphing, where you change one object into another object. We can do that very nicely by just letting, over time, the vertices of one morph or move to the vertices of another, and it's very easy to do this inside of the shader, and so this kind of action can happen in real time. A lot of these applications are of two forms. They're of moving the vertices, taking the values that come in from the application, and then within the vertex shader changing those locations. The other main area is under lighting, in that many of the things that we can do within the application can be done much better and in a much more flexible way by doing them in either the vertex shader or the fragment shader. In fact, it's more than that, because when we had the old fixed function pipeline, which was not very long ago, and probably most people still use that, you had one way of doing lighting and shading. You had one model that was built into the firmware and you couldn't change it. Now we can do very easily create either more realistic models or something we'll call cartoon shading, where you have only a limited number of colors, but you still have a light model that depends on where the light is and what the material properties are. So we'll see all of those things, and they're all done by shaders. Now, coming back to what we can do with a vertex shader, wave motion is very easy, because what we do is, as the vertices come in, we can change them in some periodic kind of way, and that's become a standard way. Many fractals can be generated inside the shader very nicely. A lot of simulations we can that evolve in time by solving ordinary differential equations for where the particles are in, say, a particle simulation, can be done again within the shader, which frees up the CPU to do other things for the application. Well, let me give you one picture here. One or two pictures of some of the differences. Here's something you couldn't do before. You could do some vertex manipulation in the vertex shader, but you really had no ability to do any of that in the fragment shader. And here's the famous Utah teapot we'll use as examples a lot in the course. It's a bunch of Bezier surface patches. And the important thing in this example is to look here at the specular component, the part that looks very reflective like a mirror. And you see that with per vertex lighting, where you apply a model to every vertex as it comes into the vertex shader, the highlight gets kind of blurred around both in the spout and on the body. But if you can do that on a fragment by fragment basis, which was only possible before programmable shaders to do offline, you do it very slowly. Now we can do it in real time, and notice you get this very, very narrow highlight, and you can see a little bit here on the spout how the highlight comes out much nicer. Couldn't do that but before. Here's another example with texture mapping. We'll spend a lot of time on texture mapping in the middle of the class, but here's just three of the kind of effects, well, two of the kind of effects. This one is how you do shading with very smoothly. Here's now you can apply an image. The image might have been obtained by getting an image of the room with a real camera or a virtual camera and then pasting it on. And here we change the surface on a sort of a fragment by fragment basis by manipulating the direction of the surface through the normal. Again, these are things, both of which happen in the fragment shader, and until they were programmable, we couldn't do those kinds of things in real time. Okay, so writing shaders historically, as we said, the first programmable shaders were there. They've been there quite a while, but they weren't very easy to use because they were programmed in like assembly language. There was a language for them, but it wasn't very easy to use, and you had to write. And how many of us write assembly code anymore? OpenGL has an extension mechanism, so even before the programmable shaders and the shading language became part of the core implementation, we were able to use some extensions which were supported on many systems to do some fragment, to write simply some vertex and fragment shaders, but we were restricted to those systems that supported the extensions. Typically, there were things like NVIDIA would have an extension that said if you're using an NVIDIA GPU, then you can use this extension. Then came along CG, which stood for C for graphics, that came from NVIDIA, which gave you a very nice programmable language for doing things, but it only worked at that time on NVIDIA cards, and it worked on Windows systems through DirectX. It was a little bit more complicated than we might have liked, and that's been subsumed by the OpenGL shading language, which at first CG could do things that a GLSL couldn't do. But as things have evolved, pretty much everybody's using the OpenGL shading language. Now, officially, it became available in OpenGL 2.0. As we've said before, it's very C-like with some extra data types for matrices and vectors. Samplers are something that we'll be using to do texture mapping. And as we've said again before, when starting with 3.1, including WebGL, every application must provide at least a fragment shader and a vertex shader. There's some newer kinds of shaders that have become available in versions of OpenGL starting with 4.1 and 4.2, but they're not yet available in WebGL, and so we'll just talk a little bit about them later in the course. So here's your simple shader that we've seen, and let's just go back over the key words here. First, that attributes are things that are sent from the application to the vertex shader. So they include the necessary one, namely the position, but also others like color and later texture coordinates. And when we do shading and lighting, we'll send along normals to the surface to describe it. But for now, it'll probably be positions and colors. I'm going to talk a little bit about naming variables and give you a suggested convention in another lecture or so. Reason being that we're dealing with three different entities, each of which is a complete program, a vertex shader, a fragment shader, and the application. And things like positions and colors can appear in all three. And I want to give you an application, or give you a convention that hopefully will make things a little bit simpler in what we've adopted in the book. Each is a complete program. You need this void. You don't really need this void over here. There's a built-in variable. Built-in variables always begin with GL underscore and GLSL, but most of them were deprecated with OpenGL 3.1. The couple that are left that are going to be important to you are GL position and GL frag color. For the fragment shader, GL position is the position and clip coordinates that must be the output of every vertex shader. It's called a built-in variable because you don't have to declare it the way you have to up here for V position. So here's a simple, again, pass-through shader that just sends out what it comes in. Doesn't have to do any changes in the coordinate system. Okay, well, here's the execution model. The applications program really has a couple of jobs. One is it has to send data to the GPU. The data is the shader program has to be loaded in a separate step, and then as another separate step, we send the vertex data over to it. So that was the part that said allocate a buffer on here and now place the data that I just computed inside of my application onto that buffer. But then to execute the code on the vertex shader, we usually do it through just one function, GL draw arrays, that says draw the information that now is inside of those active buffers on the vertex shader, and what comes out is a stream of vertices. So in some ways, it's vertex in and vertex out, plus you have to send in the program and a control function that says, okay, now's the time to draw the information that's on there. Remember, this is retain mode graphics so that the data are there and that repeated executions of GL draw arrays will cause repeated drawings or repeated outputs, or let's put it this way, repeated execution of the vertex shader. Now, to be a little more correct here, an execution of the vertex shader occurs for every vertex that comes out. So there, you do an independent execution of the shader program for every vertex coming from the application program. And if you have any kind of a modern GPU, that GPU has multiple units in it, each of which can be a vertex shader. So there's a lot of concurrent execution going on inside of our GPU through multiple executions of the vertex shader and multiple executions of the fragment shader. Another thing that we're going to talk about in a little while is when things can change. When, if there are some constants or parameters in here, when can we change them? Can we change them on a per vertex basis? Can we only change them on a per primitive basis, on only for a whole triangle or some other entity? And we'll talk about that in a little bit. But you execute the vertex shader, its output, which is each one outputs one vertex, and those vertices go on to the primitive assembly stage, which says, now I know that you send a triangle, so I have 3 vertices. I'll put those together and send the information on to the rasterizer. So here's the trivial, now here's a trivial fragment program, which we've seen before, that all this is doing is setting every color it outputs to red. That's the job of the fragment colors, to output a color for each fragment. It may do a few other things, but it must output something in GLSL, which is called GL frag color. Again, it's a built-in variable because of the GL underscore. We don't have to declare it. We once more don't really need this void here. And this is a difference between GLSL running on WebGL and GLSL on desktop OpenGL. Is you must in WebGL have the precision. Even though the default is medium precision, you must have a precision statement in here, and that's because that this comes from OpenGL-ES, which had to support a variety of low-power devices, many of which were unable to have really high precision floating point available on them. Okay, now here's the execution model for the fragment shader, and it looks something like what we had from for the vertex shader. The shader program comes from the application, but the data is coming out of the rasterizer. So the vertex shader's back here, primitive assembly's back here. That's sending it's sending vertex information to the rasterizer. At this point in the development of graphics, the rasterizer is something you're not allowed to play with. Its job is to produce fragments from assembled primitives from vertices and output all of the fragments that are inside of that primitive. All the ones that connect two vertices if it's a line segment, that fill the inside of a polygon if it's, say, a triangle. And just as with vertex shaders on a modern GPU, we'll have multiple fragment shaders executing at the same time, and each one is going to output a fragment. Well, there's a potential that a fragment can be discarded here, but what we'll mostly see is that the fragments that come out, every fragment that comes in is assigned a color and its output. There's a stage in here that I really we'll talk about later. But for example, hidden surface removal will say, oh, that fragment is hidden by something I've already seen, so I'm going to throw it away. It doesn't happen in the fragment shader. It happens down after the fragment shader along its way to get to the frame buffer. So there's some operations that you can't control very well that go on here. The most important being that hidden surface removal is going on in between the fragment shader and the frame buffer. Okay, so let's take a little break here, and then we'll look at more detail in the next lecture.